Greetings to all the space science enthusiasts out there. That's one small step for a man, a giant leap for mankind. These were the golden words spoken by Neil Armstrong when he became the first human to step foot on Moon. Humans' quest to understand what lies beyond what he sees on Earth has given birth to an incredible technology of what we today call as rocket science. In this session, I will try to take you on a journey to one of the most fascinating arenas of rocketry, which is nothing but rocket propulsion. My name is Vishak Shashidharan, and I work as a propulsion engineer at Liquid Propulsion System Center, the propulsion wing of ISRO located at Thiruvananthapuram, Kerala. You all may be wondering, what are these propulsion systems and why are these propulsion systems unique, right? Well, propulsion systems, as the name suggests, consists of a number of systems which together pushes the rocket beyond the clutches of gravity and atmospheric drag. You all may have witnessed a rocket launch at least once in your life. And all the curious minds out there would have wondered, why is there so much fire and flames and smoke coming out of the rocket when it lifts off? Well, these exhausts that you see are the byproduct of the rocket propulsion system. It is these exhausts that help the rocket go beyond the pale blue sky. Generation of such hot exhaust gases through the mixing of fuel and oxidizer in the right ratio to produce thrust which will lift up the rocket and will help launch the satellite to a precise orbit. This is what rocketry is, and this is what we do here. Today, in this session, I will try to explain rocket propulsion in the most simplest manner possible. And though people say rocket science is difficult, today I will try to make rocket science a bit more simpler for you. So today, let's start by understanding how the engines in your cars or other automobiles work. So these engines are basically called internal combustion engines or IC engines. So the petrol or diesel that you fill in your cars are basically acting as a fuel. And this fuel is sprayed into these engines and gets ignited. And that ignition creates thermal energy. This thermal energy is then converted through gears and cams into mechanical energy, which then you see as your tires rotate. So, in a nutshell, IC engines basically convert the chemical energy that the fuel has into thermal energy and then into mechanical energy. But, do you think a rocket which weighs around 200 ton in mass, can an IC engine lift a rocket? Well, the answer is no, and hence the need for a new engine or the rocket engine arises. IC engines cannot be used for powering rocket engines. The three-step energy conversion process in IC engines reduces its efficiency. Also, the power generated by an IC engine is directly proportional to its mass. Bigger the power, heavier the engine. In comparison to general transportation carriers, rockets are huge. It becomes nearly impossible for an IC engine to deliver the push required to lift the rocket. It was then that scientists developed another method to obtain the thrust required for rocket engines. This method was a direct application of Newton's third law, which is every action has an equal and opposite reaction. The chemical energy stored in fuels are ignited and these hot gases are pushed out of the rocket, which provides an equal and opposite force. So, in rocket engines, the chemical energy is converted to thermal energy and this is directly converted into the required thrust for lifting the rocket. There is one more major difference seen in rocket engines. As you know, rockets fly high beyond the bounds of Earth's atmosphere.
the oxygen required for combustion of fuel is unavailable in these regimes of rocket flight. So, rockets are forced to carry the required oxygen or chemicals that generate oxygen along with it. These chemicals that provide oxygen in chemical reactions are known as oxidizers. So, rockets carry both fuel and oxidizer during flight. Conventional fuels used in our day-to-day life will not be able to provide the energy required to lift these massive rockets. So, in rockets, special kinds of fuel called propellants are used. Propellants are classified based on the state in which they are stored inside the rocket. We have solid, liquid, and cryogenic propellants. Obviously, solid rocket stages have propellants stored in solid state and liquids have propellants stored in liquid state. You may wonder what cryogenic propellants are. A rocket stage where the propellants are stored at very low temperatures are called cryogenic propellants. The word cryo in the term cryogenic represents extremely low temperatures. Let us learn about solid propellants first. As the name suggests, solid propellant use solid oxidizer and fuels which are stored in solid state. In solid stages of ISRO, finely powdered aluminium is used as fuel and a chemical called ammonium perchlorate is used as the oxidizer. Both these ingredients are powders. To convert them into a block of solid, we use a synthetic rubber called hydroxy-terminated polybutadiene or HTPB in short. Like all rubbers, HTPB is a polymeric liquid. Precise quantities of finely powdered aluminium and ammonium perchlorate are added into this liquid. The mix is stirred using mechanical stirrers for days at a time. This ensures proper homogeneous mixing of fuel and oxidizer in the mix. The thick slurry is then poured into molds containing coagulating chemicals. These additional chemicals kickstart a polymerization reaction leading to the conversion of liquid HTPB to solid HTPB impregnated with propellants. This big block of solid propellant is called as a grain. The solid propellants are ignited using specially designed igniters and the thrust is controlled by properly sizing the grain structure. Solid propellants, once ignited, cannot be extinguished.
Now you would have got a small glimpse of how a solid rocket motor works. And you would have already understood that there are basically two disadvantages for a solid rocket motor. The first one being it cannot be controlled. You have a thrust profile which is given and that is something which happens in flight. You have no control over the solid motor rocket. The second major disadvantage is that the solid motor cannot be stopped at will. That means it will fire till it is exhausted completely. And this is one major disadvantage that is there for a solid rocket motor. Because as I've already said, a satellite must be injected into a precise orbit. And with a solid motor, it is not possible to precisely inject a satellite into an orbit. Hence the need for liquid rocket engines come. So liquid rocket engines are basically engines where propellants are in liquid state. So just like how we use petrol and diesel in our cars, we have different fuels and different oxidizers which are in liquid stage. So you might have seen the engines that are there behind me. These are a series of engines that we have here at ISRO and all of these are liquid engines. So let's go into the first engine. This engine is this is one of the most simplest liquid engines that we have in ISRO. This is the Ps4 engine. Ps4 in the sense, it is the engine that propels the fourth stage of PSLV. So in PSLV, in the earlier videos you would have seen, there are basically two stages which are liquid engines and this is the fourth stage.
Ps4 engine was the first liquid rocket engine to be developed and flown in India. This engine is a simple pressure-fed engine with regenerative cooling mechanism. Pressure-fed engines are rocket engines where propellant stored at high pressures in tanks are simply expelled through a nozzle after combustion. Though these engines are simple and easy to develop, they cannot produce very high thrust. So, such engines are usually used in upper stages of rockets where thrust requirement is low. Ps4 engine works with MMH, that is, monomethyl hydrazine as fuel and mixed oxide of nitrogen as oxidizer. It develops a thrust of 7.33 kN when operated at a chamber pressure of 8.3 bar. This engine has multi-restart capabilities which also enables PSLV to undertake multi-orbit missions.
So, if you have noticed, in this engine, there are basically three major segments into this engine. First are these two valves, second is this thrust chamber, and third is the diversion pump. These valves are responsible for injecting the fuel and oxidizer into an injector head where the spraying of both the fuel and oxidizer happens. And once the injector sprays the fuel and oxidizer into the thrust chamber, combustion takes place and hot gases are produced in this segment. And the hot gases that are produced in this segment move down through the nozzle in supersonic speeds, and then it moves to the diversion part and then goes out of engine. So this is the basic working of this engine. Now, you would have noticed that there are two segments over here. One is this thrust chamber plus nozzle segment, and there is a black colored diversion segment. You would wonder why there are two segments in this. Basically, this engine is not just used in the fourth stage of PSLV. It is also used as a steering engine in PSLV in the first stage. It is known as RCS, Reaction Control System.
What you just saw is a ground test firing of RCS engine. You would have noticed the engine gimballing to almost 45 degrees to the right and left. The angular movement of this engine is in fact used to steer PSLV during its first stage. Next time you watch a PSLV launch, stay tuned for liftoff minus 3 seconds where you will see RCS engine firing.
I hope you have understood how the Ps4 engine works a bit. Now let's move on to a bigger rocket engine, a bigger liquid rocket engine. The engine that you see behind me over here is called the Vikas engine. And this engine is responsible for lifting the second stage of PSLV. It is also used in GSLV Mark II as the strap-ons and in GSLV Mark III in the L110 stage. So, just to give you an insight of how massive this engine is, you might be knowing the buses that you normally use around 8 grams of petrol or diesel to run. But this engine over here ejects out around 298 kgs per second, while the bus was just 8 grams per second. So now you can imagine how massive this Vikas engine is. This Vikas engine, when compared to the Ps4 engine, is a pump-fed engine, unlike the Ps4 engine which was a pressure-fed engine. So the pumps that you see on top, the UDMH pump and the N2O4 pump. UDMH is basically the fuel that we use for Vikas engine, and N2O4 is the oxidizer that we use. And the pumps that you see on top is responsible for pushing the fuel and oxidizer into the thrust chamber and then later onto the nozzle.
Vikas engine was developed by ISRO in consortium with the French Space Agency during the 1980s. This engine is capable of generating a vacuum thrust of 800 kN while operating at a chamber pressure of 58.5 bar. Vikas engine works on gas generator rocket engine cycle. In Vikas engine, turbopumps are used to pump propellant stored at low pressures in tanks to very high pressures before being injected into the thrust chamber. The pumps are run using a gas turbine, which in turn is powered by hot steam from gas generator. The gas generator in fact burns small quantities of UH25 and N2O4, and water is sprayed to produce superheated steam. Rocket stages using Vikas engine hence needs to store water as the third propellant. Vikas engine is the workhorse of ISRO, which is being used in all presently operational rockets.
Now I have explained two liquid rocket engines to you. One the Vikas engine and the other the Ps4 engine. Now you may ask me, are these the most efficient engines that we can make? Well, the answer is no. The most efficient engines are those engines which use liquid oxygen as the oxidizer and liquid hydrogen as the fuel. And these engines are called cryogenic engines. You may have heard that India has mastered the technology of cryogenics, and I will show you one such engine which we have indigenously developed in ISRO, and this is called the Cusp Engine. Cusp in the sense it is cryogenic upper stage engine. This engine, though initially we had bought it from Russia, we then developed and indigenously mastered the technology of cryogenics. This engine is used in GSLV Mark II as the upper stage engine.
Plus 5 seconds. Plus 1 minute 15. Plus 3 minutes 10 seconds. 20 seconds.
This is the nozzle exhaust of one of the biggest cryogenic engines that we have in ISRO. This is the CE-20 engine. CE-20 engine is the first cryogenic engine that ISRO has developed from the scratch indigenously. CE-20 engine is used in the upper stage of GSLV Mark III. The engine that you see behind me is an actual engine. We have now seen a number of engines that we use in the launch vehicles or the rockets that we use in ISRO. But propulsion systems are also used in satellites, like the one which you see on my left, Mars Orbiter mission. Propulsion systems are required in satellites because of two major reasons. The first reason being, satellites require orbit racing maneuvers to be carried out. And the second reason being, satellites require steering accuracy. That is, the satellites must be steered into a particular direction to get pointing accuracy. So for these both reasons, we use different propulsion systems in satellites. The engine that you see to the left of me is called the LAM engine. This LAM engine is used for orbit racing maneuvers in satellites. The LAM engine has a thrust level of 440 Newton. Now if you look to my right, you will see the AUCS thruster. This thruster is of just 22 Newton, and these thrusters are used in multiple numbers to steer the satellite to the orientation that is required. We have now looked into the propulsion systems that we use in launch vehicles and in satellites. The system that you see to my right is very unique in nature. This system was basically developed to assist satellites and take those satellites to its intended orbits. This system that you see on my right was developed by ISRO indigenously for a foreign customer. It was developed, it was qualified, and it was tested. This system is called the Payload Assist Module for GSL, or also known as PAMG. Now we've seen a wide variety of engines. You saw a lot of liquid engines, you saw solid engines, and you even saw cryogenic engines. Now, you know these engines use the fuel and oxidizer and make thrust. But where do you store this fuel and oxidizer? So that is where a stage comes into play. A stage is where you store all these tons of fuel and oxidizer in different tanks, like the one you see behind me. This stage is the upper stage of GSLV Mark II. Upper stage of GSLV Mark II, if you remember right, it was a cryogenic stage and it uses the cryogenic engine.
It is in stages like these that propellants are stored and expelled into the engine. Stages consist of propellant storage and servicing systems like tank pressurization systems, command system modules, and control system modules. These systems together supply propellant and oxidizer at required pressures to engine pumps.
Through this episode of the video lecture series, you would have got a basic understanding of how different propulsion systems for rockets in ISRO work. You have seen a number of engines and different types of engines that we use in ISRO. You have also seen a stage where we store the propellants. It is not only these technologies that we are developing right now. There are technologies like the semi-cryogenic engine, the ion thrusters that ISRO is developing at present. These technologies will play a key role in the development and flight of future rockets and will be a crucial part in nation building. This is Vishak Shashidharan signing off. Thank you.